Hello, welcome to lecture 2 of module 2. In the previous lecture, we got an overview of very brief overview of circuit quantum electrodynamics, and we got introduced to the concept of Cooper pair box. In this lecture today, we learn how to model a Cooper pair box as a two-level system, and also you will be introduced to the idea of transmission line, which is a must-learn topic for circuit quantum electrodynamics. So let us begin. In the last class, we started discussing Cooper pair box. A Cooper pair box consists of two superconducting islands placed close to each other. Typically, a Cooper pair box has the dimension in micrometer and the gap between the island is in nanometer. We learned how to write down the model Hamiltonian for a Cooper pair box in the last class. Here, the first term refers to charging energy, and the second term refers to or it denotes the energy involved in tunneling of Cooper pairs from island 1 to island 2 or from island 2 to island 1. QZ is the gate charge here, and EJ is the Josephson energy. Then the question was how to solve this Hamiltonian and mainly how to realize a two-level system out of it. In the first step, we took tunneling as a perturbation and ignored it. We simply considered this first term of this CPB Hamiltonian. We wrote the charging part of the Hamiltonian in a more convenient form by expressing this charge operator in terms of the number operator while expressing the gate charge in the similar form. Okay, and we wrote down the charging part of the Hamiltonian. Here EC is the charging energy constant. NG is the controllable parameter as it is related to the gate voltage or the external electric field that is used to tune the Cooper pair box. We plotted the charging energy and as a function of the controllable parameter Ng, and keeping this Cooper pair, number of Cooper pair to be fixed, we find that in the absence of perturbation, various charging energy states cross each other. For say Nz lying between minus half to plus half, the preferred ground state energy state is N is equal to 0, while for Nz lying between say say plus half, okay, plus half to plus 3 by 2, the preferred ground state energy corresponds to N is equal to 1 and so on. We basically get a set of or array of parabolas for various Cooper pair, various number of Cooper pairs. Now in the second step, we switch on the perturbation. That means we consider the second term in the Hamiltonian, and we must have charging energy should be greater than the Josephson energy. Clearly, as we discussed in module 1, the energy states no longer cross each other, they simply turn into avoided crossing, as I have depicted this in this picture. As you see, the energy level no longer cross, so we get into this is avoided crossing. Okay, this is what I mean by avoided crossing. Now next what I will do is that we are going to focus around one of the degeneracy points. Say for example, let us focus around Ng is equal to half. Then we will restrict ourselves to the energy levels N is equal to 0 and N is equal to 1. As you can see, when Ng is equal to half, when perturbation was switched off, these energy states corresponding to n is equal to 0 and n is equal to 1 cross each other. So if I focus around Nz is equal to half, then we are actually confining ourselves to the charged energy state n is equal to 0 and n is equal to 1. And another thing you can see that all the other energies will be far off and their effects will be small. Now near Nz is equal to half, we can expand the charging energy 4 EC into n minus Nz. Let us expand it near the okay, let me write here, expand the charging energy near Nz is equal to a half. If we do that, what I mean to say is that let us say Nz, replace it by half plus some deviation from Nz is equal to half. So delta Nz is the deviation from Nz is equal to half. Then we can write n minus Nz square is equal to n minus half minus delta Nz whole square. Now you recall that this n can be 0 or it can be 1, okay, because we are around near Nz is equal to half. So for n is equal to 0, we'll get 1 by 4 plus delta Nz square. This is for n is equal to 0. And if we take n is equal to 1, then we'll get 1 by 4 minus delta Nz plus delta Nz square. This is for n is equal to 1. So this positive sign or plus sign refers to the state n is equal to 0, or you can remember it just like thinking that, okay, you can, as you can see that you are having a positive slope here for n is equal to 0, that's why you are having a plus sign for that, and for n is equal to 1 you are having a negative slope for the minus sign. Okay, plus sign refers to n is equal to 0 and minus sign refers to n is equal to n is equal to 1. Okay, we are going to neglect this delta Nz square term because we'll focus only on the linear term, that is the linear curvature around delta Nz is equal to half. So we will just focus near this region only, so around the linear curvature region. And then we can write the charging energy ECH is as 4 into EC 1 by 4 plus minus delta Nz. Let me emphasize once again that plus correspond to n is equal to 0 and minus correspond to n is equal to 1, or I have EC plus minus EC 4 EC into delta Nz. Now this term is basically a constant, it is simply energy offset, so we can ignore this constant term as well. So if we ignore that, then we will have the charging energy as plus minus 4 EC into delta Nz. Recall that delta Nz basically is the controllable parameter which you can vary. Now clearly for n is equal to 0 state, in the absence of perturbation, that correspond to this energy eigenvalue for this energy state would be simply 4 EC delta Nz, and for n is equal to 1 state, the energy eigenvalue would be minus 4 EC delta Nz. Alright, now let us take Nz, this state state as 1 0, and n is equal to 1, let me write it as 0 1. Then now let us switch on the tunneling term, and in the presence of the tunneling, the Hamiltonian can be now written like this. So we'll have 4 EC delta NZ in the basis n is equal to 0 and n is equal to 1, get n is equal to 0. Okay, let me write it this way. This is for this energy corresponds to n is equal to 0. So this term and 4 EC delta NZ get 1 bra 1, and the Josephson tunneling part is going to give rise to this term get 0 to 1 and get 1 to this. Alright, so therefore immediately we see that we are actually getting a two-level system Hamiltonian, and which can be expressed in the matrix form by this 2 by 2 matrix. We have 4 EC delta NZ, and here minus EJ by 2 minus EJ by 2 minus 4 EC delta NZ. So that's how we obtained a two-level system out of a Cooper pair box if we focus ourselves near the degeneracy point NZ is equal to half. Now we know very well how to solve this 2 by 2 Hamiltonian. The energy eigenvalues we can write easily from our knowledge of module 1. That would be plus minus, we'll have EJ square by 4 plus 16 EC square delta NZ square. Just like in the case of two-level atom or two-level system that we discussed in module 1, here also if we plot energy eigenvalue as a function of this controllable parameter delta NZ, we will get a typical plot like this one. So it should remind you about the two-level system that we discussed in module 1. You see, when the perturbation is not there, these energy levels, these two energy levels cross each other at this point, and that is called the degeneracy point. NZ is equal to half, that is delta NZ is equal to 0 or NZ is equal to half. This is the degeneracy point, and the positive slope refers to the eigenstate for n is equal to 0, and negative slope refers to the eigenstate corresponding to n is equal to 1 state. And when the perturbation is switched on, they no longer cross. This plot I am drawing for near NZ is equal to half. Okay, you just have to remember that. So and this energy gap, that is EJ by 2. This is also EJ by 2, and this particular point correspond to here the state. This particular point correspond to the state 1 by root 2 n is equal to 1 minus n is equal to 0, and this one correspond to the state 1 by root 2 n is equal to 1 plus n is equal to 0. Alright, so I encourage you to actually work out it in the similar way that we have done it for two-level system, and then you will get it. Okay, so please do that. So we have learned about Cooper pair box, also known as charge qubit. As I said earlier, the typical size of a Cooper pair box is in micrometer range, and these Cooper pair box are fabricated using lithographic techniques. In fact, these same lithographic techniques are used for computer chip production. The typical material used for Cooper pair box is aluminum, and you may know that the aluminum has a transition temperature in the range of 1 Kelvin. So clearly this implies that Cooper pair box has to be operated at very low temperature, and in typical experiments for better or strong superconductivity, scientists or experimentalists generally work at the temperature of 20 millikelvin, which is far below than the transition temperature, and T is the operating temperature of a Cooper pair box. Okay, and because at this temperature superconductivity is very good, the typical charging energy is on the order of, you remember EC is equal to QE square by 2C. So this is typically in the range of 100 micro electron volt, and if we can convert it to temperature as well, because you may know that the 1 electron volt is equivalent to around 10 to the power 4 Kelvin. So EC in temperature, it would be equivalent to around 1 Kelvin. On the other hand, the Josephson energy EJ, okay, is in the range of 20 micro electron volt. So as you can see here, that EC is 100 micro electron volt and EJ is 20 micro electron volt. So therefore EC is greater than EJ, and that is needed because, as you saw earlier in our analysis, that Josephson part in the Hamiltonian, we took it as a perturbation. Now interestingly, you see the energy gap between the two energy levels at this degeneracy point Ng is equal to half is EJ. Okay, so that is going to be very important. So this energy gap is EJ. Now the operating temperature is 20 millikelvin. So the thermal energy corresponding to this operating temperature is in the range of, if you put the values there, this Kb is the Boltzmann constant, then you will get it to be 2 micro electron volt. Now this thermal energy is obviously less than this Josephson energy, that is this gap between these two energy levels. So the thermal energy cannot initiate transition between the energy level, and that is good because then we can consider this system as a quantum system, and thermal energy is not going to play any unwanted role here. Now we can very easily find out what kind of radiation is needed to couple a Cooper pair box. So what I mean to say is that what kind of electromagnetic radiation one has to irradiate to this Cooper pair box. So obviously this radiation energy, say h cross omega, has to be equal to this gap, that is EJ. So you just have to solve this equation. H cross omega is equal to EJ. You know H cross is a reduced Planck constant, and if you EJ is already, we see that that is 20 micro electron volt. So if you put down all the parameters here, so omega would turn out to be around 2 pi into 5 gigahertz. Okay, and just by the way, 1 gigahertz is equal to 10 to the power 9 hertz. Now you may know that gigahertz frequency are nothing but microwaves. In fact, 1 gigahertz is corresponds to actually 30 centimeter. You can convert this frequency into wavelength using this relation. Lambda is equal to c by nu. Nu is here 5 gigahertz, and c is the speed of light in vacuum, that is 3 into 10 to the power 8 meter per second. If you put down the numbers there, you will get that 1 gigahertz is equivalent to 30 centimeter. So if we are to couple a Cooper pair box device or charge qubit device to radiation, the radiation must be in microwave. Okay, so let me write here, if we are to couple a CPB or charge qubit CPB device to radiation, the radiation must be a microwave. Okay, before I go further, let me quickly give you some important information about Cooper pair box. So first of all, what is the circuit representation of a Cooper pair box? Okay, let me do it here. So is Cooper pair box or a charge qubit can be depicted by this kind of a circuit. I will explain. So you have this gate capacitance here, and then you have this Josephson junction. This big cross denotes Josephson junction. This actually represents Josephson junction. Okay, and then you have this gate voltage, and then you connect it to the Josephson junction, and the island is formed by the superconducting electrode. Let me show it by this dotted line here, by this superconducting electrode. Between this is the gate capacitor and the junction capacitance. Okay, so this is how a Cooper pair box is represented in a circuit. So this is the gate voltage. And this gate voltage controls the chemical potential of the island, and chemical potential is, as you know, it is related to the number of Cooper pairs. In Cooper pair box, actually the charge contribution to the energy dominates over the magnetic flux, as we will see later, and this is why Cooper pair box is referred to as charge qubit. Let me repeat again, in Cooper pair box the charge contribution to the energy dominates over the flux, magnetic flux, and this is why Cooper pair box is referred to as charge qubit. And we will discuss about other forms of qubit or two-level system in circuit QED later on. Now let us discuss how we can obtain an appropriate microwave cavity, because we want strong interaction between the microwave and our two-level system, for which we need to put the qubit or two-level system inside a cavity. So what I mean to say is that in order to enhance interaction between a Cooper pair box or two-level system or the ones that we encounter in circuit quantum electrodynamics, it is better to put the qubit or the two-level system inside a cavity, because that will ensure longer interaction time, and also it will enable us to have higher intensity of the microwave radiation inside the cavity. But before discussing microwave cavity, let me remind you about optical cavity, to which most of you may be familiar. For example, I am actually referring to the so-called Fabry-Perot cavity. You know that the Fabry-Perot cavity consists of just two fixed mirrors separated by some distance, say d. Okay, and one of the mirror is perfectly reflecting, and another mirror is partially reflecting. Say this mirror say this mirror is partially reflecting, and this one is perfectly reflecting or completely reflecting. So say if light is incident on this particular mirror, the light of wavelength say lambda, it can enter into this cavity, then after entering into the cavity it would get reflected from this perfectly reflecting mirror, and then it will again hit this partially reflecting mirror and it may actually come out. Okay, so that is the idea here. But not all wavelengths can enter into this Fabry-Perot cavity. Only those wavelengths which satisfy this particular condition, say the length of the cavity, the distance between these two mirrors, has to be an integral multiple of the half wavelength, which you may know already. That means that basically it has to satisfy this condition twice into the cavity length into lambda, and using this you can actually write about the corresponding frequency. Only certain wavelengths or frequencies are allowed. You can easily work out that the angular frequency if of this type can only be will be able to enter into the cavity. So this condition, or in terms of frequency, you may know this well-known expression. So whenever these conditions are satisfied, the light of frequency nu or angular frequency omega would be able to enter into the cavity. Just to remind you that omega and wavelength, angular frequency and wavelength are related by this expression. Suppose the medium inside the cavity is air, so n is equal to, or refractive index is equal to here 1. Okay, so by the way, we require bit of familiarity with Fabry-Perot cavity while discussing optomechanics in module 3. Now for optical radiation in a typical Fabry-Perot cavity, the wavelength is on the order of micrometer, and the typical size of the microwave cavity, one-dimensional microwave cavity, is on the order of centimeter. In typical experiments, people generally shoot neutral atoms. Let me explain that. Suppose you have a Fabry-Perot cavity like this, these two mirrors, and then say an optical radiation is inside this. This is the envelope of the optical field, and the wavelength is in the micrometer regime. And what people do, so this is in centimeter, what people does is they throw or shoot neutral atoms into this field, okay, from any side, any direction, neutral atoms to the optical cavity, and study their interaction with this electromagnetic radiation. So this is our electromagnetic radiation, so, and this is our neutral atom. So it is thrown into this radiation there, or sometimes atoms are kept inside this cavity, and then interaction between the electromagnetic radiation and the atom is studied. You may know that in most neutral atoms, the usual transition wavelength, suppose you consider a two-level atom, natural atoms I am talking about, a two-level naturally occurring atom, not artificial atom, usually the transition wavelength is on the order of optical wavelength or optical frequency, say 10 to the power 14 hertz. So omega is on the order of 10 to the power 14 hertz. So okay, but so in that case, clearly the Fabry-Pérot cavity are suitable resonator for studying strong atom light interactions. However, for our case, we are interested in the wavelength of the order of centimeter, because already I discussed about it. So microwave, when we talk about microwave, its wavelength is on the order of centimeter, or frequency is in the microwave, that is in the range of gigahertz, or that is 10 to the power 9 hertz, unlike the optical frequency, which is 10 to the power 14 or 10 to the power 15 hertz. So it will be definitely much more convenient to have a microwave cavity, and but that microwave cavity should be on a directly on a chip. Okay, microwave cavity, we want a microwave cavity on a chip, because as you know, we already have our Cooper pair box that is embedded in a chip, as I discussed earlier. And we can actually get a microwave cavity by using the so-called transmission line. So if we use transmission line, we'll be able to get microwave cavity. But however, actually, to get a good idea, it would be better for me to first discuss about waveguides for microwave radiation. So let me discuss briefly about waveguides. And all of us know a typical waveguide is the so-called optical fiber, but that is for optical radiation. And in these optical fibers, as you know, that an optical fiber is basically made up of glass or silica, and some light can travel inside this optical fiber because of the so-called total internal reflection phenomena, loosely speaking. Okay, light is guided inside it, and optical fiber is a dielectric. But we are going to deal with microwaves, and microwaves, as you know, that we cannot use glass fibers, because microwave would get absorbed inside the optical fiber. It will not be able to propagate inside an optical fiber. And we know that the microwave frequencies actually can pass through metals, so we have to consider metallic waveguide. So rather than dielectrics, we have to deal with metallic waveguides if we want to transmit our signal or using microwave, or if we are interested in transmitting microwave signals, better use metallic waveguides. The simplest metallic waveguide we may consider a simple wire, a simple metallic wire. Okay, let us understand how a wave can propagate inside such a wire. So we are just considering a single metallic wire. Let me briefly talk about the physics, that means how a metallic wire can support a propagating wave. To understand that, let us assume that we have a metallic wire like this, and at some instant of time positive charges are created in is a collection of charges are basically created. Positive charges or negative charges like this are created inside the metallic wire, okay, by some mechanism. So as you can see, because of this, what is going to happen is that electric field lines would be generated. So electric field lines like this would be generated. These lines will go from positive charge to the negative charge, okay, positive to negative, like this we'll get these fill lines, okay. So okay, we have here plus minus like this. I hope you are getting the idea here. These electric fields, would have a tendency to push the charges or charge distribution to spread out, and this is because of the repulsion, like charges repel, these negative charges will repel each other, positive charges will repel, and because of this pushing, this charge distribution would spread out. As these charges start moving, it will result in current, and which in turn will result in magnetic fields, okay. Because of that, it will result in magnetic field. And just this is for, it's not rigorously correct, just I'm giving you an idea. So magnetic fields are going to be generated because of the generation of this current, and as these magnetic fields build up, this changing magnetic field will create again electric field, which will act against this original motion. So a kind of couple dynamics between electric and magnetic field, okay, electric and magnetic fields will occur, B fields will occur, and this is actually going to result in, this is going to resulting in a wave traveling along the wire. So I think you actually, most of you know how electromagnetic waves get generated, right? That is basically because of this interplay between the electric field and the magnetic field. So this is the same thing here, only here is that the wave that is getting generated is a microwave. So a wave would be result, and it will propagate along the wire. But this kind of actually waveguides are not practical. The reason is, we are not going to the mathematical analysis. I will just tell you the reason why. Firstly, as you can see from this diagram, that this electric field extends, actually this electric field extends too far. So far field would be there, electric fields will extend too far, and which may affect the other metal pieces that is actually in the chip, and this is going to result in dissipation of energies, and which is obviously completely avoidable, and we don't want that to happen. And this is one reason. And secondly, the other reason is the so-called dispersion. What turns out that the speed of the wave turns out to be dependent on the wavelength of the radiation, or it is dependent on the frequency, the same thing. So therefore this is of course a completely detrimental as long as we are concerned about transmitting signals, okay. So therefore the question is, what kind of waveguide would be suitable? The solution is actually turns out to be very simple. The solution is that instead of one single wire, let us take two wires, okay, parallel to each other, and this is actually going to form the so-called transmission line, and that's what now we are going to discuss. Now if we take two wires instead of one wire, the field, suppose we create such distribution like this, the field will be strong in between these two wires, and there would be very little field outside actually. So very little fields, I should say very little stray fields outside, and moreover it can be shown that the speed of the signal is not going to be dependent on frequency or wavelength, it is going to be a constant. If you are interested in analysis of this kind of transmission line, you can look at any electrodynamics or electromagnetism book where transmission line is discussed. Actually, even better if we can use coaxial cables. Say we have a one cylindrical wire inside which is surrounded by a large cylindrical wire outside like this. So this is the wire inside, small cylindrical wire, and the another one is the bigger one, and in this case there would be actually no field at all outside. In the ideal case, only thing is that the field here would be radially outward. Field should be radially outward for this positive charge distribution, and no stray fields at all outside, of course, in the ideal case. And moreover, that the speed of the signal is also going to be constant. In fact, this three-dimensional version of the coaxial cable transmission line could be realized as a two-dimensional version of a transmission line on a chip surface. If we can imagine, say, a plane perpendicular to this wire, suppose it is cutting the coaxial cable, okay, like this. So it is going to cut these coaxial cables here, here, here. So because of this, I hope you are getting the idea, because of this we are going to get one inner wire and two outer wires, okay, and this can be actually realized on a chip surface. On a chip surface, rather than metal, we are going to have superconductors. So this is superconductor, this, and this is another superconductor. These are the two outer conductors or outer conductors, and this one you see here, this one is the inner conductor. And of course we are going to take superconductor in this case because there will be no loss, as currents can flow without any resistance. This blue colored line shows actually the insulating substrate. These are this blue portions here depicting insulating substrate, okay. And in fact, so this is the 2D version of a coaxial cable transmission line or coaxial cable on a chip surface. However, we want to pick up a model which contains all the essential features of this system that I have described here. By essential features, I mean the followings. First of, the model that we are going to build up must contain, say, charge distribution charge distribution, because here you see we have a charge distribution like this. Say here the positive charge, negative charge, positive charge, negative charge, some kind of accumulation is there, and then here you have negative charge, positive charge, so like this. And in this other conductor here you have this negative, positive, negative, like this. So you will have field lines. Because of that you will have electric field lines on both sides here. Okay, here you will have things like this. So first of all, charge distribution, then field lines. Okay, and because of it of course we are going to have currents. So currents, so the model that we are going to now build up should contains all these things, and all these features are already there in our two wire transmission line setup that I discussed, where we had these two wires, two metallic wire parallel to each other, right? And here, as I discussed earlier, we have said this positive charge, negative charge accumulation. If it happens, suppose we can create this kind of distribution within these two wires, then we are going to have field lines between these two wires, and because these charges are going to repel each other like charges, and because of all these things, then current will flow in the wires, and because of these currents, changing currents, magnetic field would be there. Because of the changing magnetic fields, electric fields would be generated, and that's how a wave will be able to propagate through the wire. Our goal now will be to have a circuit model out of it, and this will be basically a discretized version of the problem but with very fine grit. So now we are going to discuss the circuit representation of this model. Circuit representation, and in fact it will turn out later on, you will see that this circuit representation or the circuit model is actually exact in the limit of sufficiently long wavelength or small frequency. Now having this kind of a model here, what we'll do next is let us divide this transmission line into a lots of small cells like this. So suppose I divide it into various small unit cell or cell size of say length A. Okay, each cell size has length A. Then you can clearly see that we consider each cell as if it is comprising of a capacitor. For example, if you see this cell here, okay, we can just model it by considering it as a capacitor, and I think it is easy to understand, right? Because we have this positive charge here and negative charge there, so we can model it as a capacitor. Similarly, for the next cell, if you look at it, then that is also a capacitor, so you will get a lot of capacitor out of it. And again, in order to incorporate, so this is capacitance of say capacitor sense C, and in order to incorporate the issue of current flowing and current generating magnetic fields, and time dependent, magnetic fields generates time dependent electric field, and all these things can be incorporated by introducing or incorporating it through some kind of a inductance, say L. So that's how we are going to model it. So we'll have, this is going to be our circuit representation of the model. Now in principle we should have an inductor down here as also, but it actually doesn't matter, as we can choose an effective value of inductance here to get the same result. In fact, please note that this inductance has equal value, and so for simplification purpose we are not going to put any L here. Okay, we'll keep it like this. You should note that this capacitance and this inductance and the capacitance are linear in A, that is the cell size, and that is easy to understand because if we increase the cell size then the capacitance also increases and accordingly the inductance also increases, or if you decrease the cell size then capacitance decreases or the cell inductance also decreases. And in fact some of you may guess that in the end we are going to make A tends to 0 because thereby we will get very fine grid we can achieve doing that. Now this model already contains, this circuit model contains all the essential features that we have discussed. So our goal would be to discuss or analyze wave propagation in the transmission line using this model, wave propagation in the transmission line, and then do a quantum mechanical treatment. Just let me put quantum mechanics. And then finally what we are going to do, that we are going to say cut this transmission line at say at 2 points, say at 2 points here and here, and because of that we'll have new boundary conditions and the microwave will then reflect back and forth forming standing waves inside the resonator. Okay, so finally we are going to discuss transmission line resonator. So we will take up this analysis in the next class. In this lecture we saw how a Cooper pair box can be modeled as a two-level system, and also we got introduced to the concept of transmission line. In the next lecture we will continue with our treatment of transmission line, and in fact we will do a quantum mechanical treatment in the next lecture, and we'll see how a transmission line can be quantized. So see you in the next lecture. Thank you.